As we gaze up into the night sky, we are reminded of the vastness of the universe that stretches beyond our understanding. Yet, this same universe, with its endless void and cosmic wonders, offers something truly incredible: the possibility to live in space. For centuries, humankind has looked to the stars, and today, we are no longer bound by Earth's atmosphere. We've sent astronauts to the moon, built stations that orbit our planet, and explored the boundaries of the solar system. But despite these monumental accomplishments, there is still one great hurdle that humanity has yet to fully overcome: life in space without the pull of gravity. In space, astronauts float freely, their bodies suspended in a state of near weightlessness. It's an experience unlike anything we feel on Earth. The lack of gravity offers a certain freedom, a liberation from the daily forces that shape our lives. But this weightlessness is also unnatural, a challenge for the human body. Our muscles weaken, our bones lose density, and the very fluids that circulate through our bodies behave differently. Over time, the effects of microgravity begin to take their toll. Astronauts face serious health risks: muscle atrophy, bone loss, cardiovascular changes. In essence, the human body wasn't designed to live in a place with no gravity. This is why artificial gravity is not just a luxury. It's a necessity for the future of space travel. If we want humans to live, work, and thrive in space for extended periods, we need to find a way to mimic the force of gravity. But how can we do this in the infinite expanse of space, where no such force naturally exists? The answer lies in centrifugal force. It's a fundamental physical principle that could be the key to creating artificial gravity. By spinning a space station, we could simulate the effects of gravity. The faster the station spins, the stronger the force felt by astronauts, pushing them outward towards the walls. This push mimics the gravitational force we experience on Earth, providing a downward pull that we rely on for everything from standing to sleeping to walking. It sounds simple, right? Spin a station, feel gravity. But the challenges are immense. The station's rotation must be carefully controlled, its speed calibrated precisely to create the correct level of gravity. Too fast, and the force becomes overwhelming, causing dizziness, nausea, and disorientation. Too slow, and the force isn't strong enough to counter the effects of weightlessness. And there's another complication: the design. How do you build a station that spins large enough to provide artificial gravity? How do you make the experience of walking in a rotating environment feel natural? It's a question of both engineering and human physiology, where the two must work in harmony to create an environment that is not only functional but livable. The station itself would need to be huge, large enough to generate enough centrifugal force to mimic gravity. For instance, if the space station has a radius of 100 meters, it would need to rotate about once every 30 seconds to simulate the force we feel on Earth. But it's not just about the size and speed. The shape of the station would also play a crucial role. For instance, a rotating ring-shaped or cylindrical structure would allow astronauts to walk along the inner walls as if they were standing on solid ground. The outer walls would experience the greatest gravitational pull, while the center of the station would remain in freefall, where microgravity would persist. But just because this force mimics gravity doesn't mean the experience will be identical to being on Earth. The human body wasn't designed to function under rotating gravity. Every movement astronauts make would be affected by the rotation, causing their perception of direction to shift. Even the most basic task, like moving across the room, could feel different as the centrifugal force interacts with the body's sense of balance. The Coriolis effect is one of the key phenomena that astronauts would need to adapt to in a rotating environment. This force causes objects to appear to deflect in unexpected directions due to the station's rotation. So, when astronauts try to throw a ball, they might find it behaves differently than they expect. A simple motion, like reaching for a glass of water, might feel like it's being pulled at an angle, causing even the most seasoned astronaut to stumble. Yet, despite these challenges, the potential benefits of artificial gravity cannot be overstated. One of the most significant advantages of artificial gravity is that it could allow astronauts to maintain bone health, muscle strength, and cardiovascular fitness for long-duration missions. With artificial gravity, astronauts would no longer need to dedicate hours each day to grueling exercise regimens to counter the effects of microgravity. They could move naturally, without the constant risk of their bodies breaking down due to prolonged weightlessness. Think about the possibility of a Mars mission, a journey that could take months, even years. In a rotating space station, astronauts would have a semblance of Earth-like gravity, making it easier to stay physically fit and mentally sharp. With fewer health complications, their focus could remain on the mission itself, not on surviving the harsh effects of space travel. The idea of a space station that mimics Earth's gravity also opens up possibilities for permanent human habitats in space. Imagine a rotating station with dedicated living spaces, agriculture, research labs, and recreational areas, all designed to sustain life for months, years, or even decades. In these habitats, humans could live, work, and even raise families in an environment that feels much like Earth. This vision of space colonization isn't just about surviving in space. It's about thriving in space. Artificial gravity could allow us to expand beyond the boundaries of Earth and build thriving colonies on the Moon, Mars, or even farther out in the cosmos. The possibility of having entire communities living in rotating habitats could pave the way for an era of interplanetary civilization, one where humanity is no longer confined to Earth, but an active participant in the larger universe. As we push further into space, artificial gravity might just be the key that transforms the way we think about space exploration. It's not merely a tool for astronauts. It's the foundation for future generations of explorers, scientists, and settlers to experience space as a second home. Artificial gravity represents more than just a technological breakthrough. It represents our future in space, a future where humans are no longer visitors, but permanent residents of the stars. We are on the precipice of a new era, one where space is not just a place to explore, but a place to live, to grow, and to thrive. As we embark on this journey, we will continue to face challenges, scientific, technological, and human. But with artificial gravity, we take one step closer to turning our dreams of space habitation into a tangible reality. The stars, once unreachable and cold, could soon be within our grasp, not just as a destination, but as a new home. In the end, artificial gravity isn't just a scientific challenge. It's the promise of humanity's future in the cosmos, grounded in the force that has shaped our lives since the dawn of time. The quest to bring gravity to space is not just about science. It's about securing a place for humanity in the vast expanse of the universe.